here I am on page 6, and this is assignment number 3 of the unit, and it's notes on what's called product of powers. Okay, so the first question is, what's a power? Okay, so when we have an exponent, right, we're used to, we've seen these before, like, let's say I have this 3 squared, okay? So we have 2 different pieces here, right? We have the base is in pink, this is the base, okay? We have the exponent's in purple, in this case the exponent is 2, and the power is this whole thing. So 3 to the second, that's called a power, right? So if I'm going to have a product of powers, right? Product, we remember, means multiplication. If I'm going to have a product of powers, I'm going to be multiplying 2 powers together, okay? And just to give it to you one more time, let's say I could have x to the 5th. This would also be a power, right? Again, the 5, this is the exponent. Okay, it doesn't matter that this is a variable as opposed to a number. It's still the base, right? This means x times x times x times x times x 5 times. This means 3 times 3 2 times. Okay, and this is still, this whole thing, x to the 5th, is still the power. And then let's just quickly review, like, what does this mean, right? What does 2 to the 3rd mean? What does that mean? 2 to the 3rd means 2 times 2 times 2. It means I'm taking this number and I'm multiplying it by itself 3 times, right? So it's not 2 times 3, it's 2 times 2 times 2, right? So that's 2 times 2 is 4, times 2 is 8, right? And if I have something like this, 3 to the 2nd power, if I switch those, okay, again, that's not 3 times 2, it's not 6. That's 3 times 3. It's 3 multiplied by itself 2 times. 3 times 3 would be 9. And then if we get into these like larger exponents like this is 5 times 5 times 5. And what we learned as we've gotten a chance to look at some exponents and exponential growth is this is a really big number. Okay, now you could pull out a calculator and do it, but what you need to know for now is that when I have a high exponent like this on a number, it's going to create some really big numbers. Exponents create big numbers. Okay, so now we're going to take a look at a rule called the product of powers. Okay, and here's what the rule says. And I'm going to show you a whole bunch of examples, but here's the rule. The rule is if I have a base like x to a certain exponent times that same base to an exponent, that this equals the same base again. Notice the base hasn't changed, base, all x. I'm going to add the exponents. Okay, so this is the big rule. And now we're going to take a look at it in a bunch of different ways so that you're not just memorizing a rule, you're understanding why the rule works and you're seeing lots of different situations where it works. Okay, so let's start with, let's say I have 6 to the 3rd, right, times 6 to the 5th. 6 to the 3rd times 6 to the 5th. Well, okay, so what does this mean? Okay, 6 to the 3rd means 6 times 6 times 6, right? And I'm multiplying that times 6 to the 5th. Well, what does 6 to the 5th mean? 6 to the 5th means 6 times 6 times 6 times 6 times 6. So what does this equal? Well, this equals 6 times 6 times 6, right? All of these 6s. And what I notice is that is, how many 6s is that? Well, it's 8 6s. Well, what do I notice about that? That's this 3 6s, right? That's that 3 6s plus this 5 6s And so I'm going to save myself the trouble of writing it out all the time, right? Because now I have this shortcut. So now next time I see this, do I have to write all this out? No, I know that what's going to happen is I'm going to have 3 6s and 5 6s, and I can kind of do that part of my head, and then that's going to result in a total of 8 6s. Okay. And that's true, like let's say I have something like this. 2 to the second times 2 to the fourth times 2 to the fifth. Well, what's that going to be? Do I have to write out 2 2s, another 4 2s, another 5 2s? No, I know that when I write all those out, I'll have 2 2s plus another 4 2s plus another 5 2s, and that's 2 to the 11th. And I didn't have to write all of that out, right? That doesn't make sense. I can observe this shortcut just one time and then kind of use that. Okay, and the same thing works, let's say, if this is x squared. Right here, like 2 squared, it's a number. I could figure it out. 2 squared is 4. Right? 6 to the third is 6 times 6 times 6. Okay, now I could do the math and figure it out, but that's not what we're doing right now. We're just saying, okay, what if I have a number to a power? What if I have a number to an exponent? Okay, so let's say I have x squared times x to the fourth. Okay, you're just going to look at this and say, oh, well, this is going to be 2x's times another 4x's. That's going to be a total of 6x's being multiplied together. Okay, let's look at a couple of just interesting cases you might run into. What if you have something like this? Here's a times a to the 7th. What does that equal? What does that equal? Okay, well, there's a couple different ways to look at this. One is to say, okay, here's my a, right? Here's my a. I'm going to underline it in green. That's this. Times, now I'm multiplying. What am I multiplying it by? 7 more a's. So how many a's do I have total? Well, I have this original a, right? That was 1a plus another 7 a's. So if I have something like this, this becomes a to the 8th. Okay, so what's the rule? What's the shortcut so I don't have to write this out? Okay, what you need to know is that this a, that's a to the power of 1. It's invisible, okay? So here's a rule for you to know. And I'm leaving 4 lines, please, at the bottom, right? But here, powers of 1. Okay, powers of 1. So here's what you need to know, right? Is like 3 to the first, that equals 3. So sometimes you'll see 3 to the first and you should just write it as 3. But sometimes the opposite will happen, which is like you'll see a 2 and you'll need to have a power on it for have an exponent on it for some reason, right? Like for example, in this case, it would have been nice if I had just a 1 written, then I would have been like, oh, 1 plus 7. Okay, so sometimes it'll kind of work the other way where you'll want to either take away that exponent, that invisible exponent, right? Or add that invisible exponent. And again, the same works, right? X to the first is x. Okay, n is the same as n to the first. Okay, and notice I'm writing it in both orders so you can see it doesn't matter. It doesn't matter whether it's written or not. These two things are equal. These two things are equal. Okay, so like for example, in this case, if I got a problem like this, I probably would just fill in the 1. I would just like write it like that because it would just make my life a little easier. Okay, so that's kind of one interesting case you might run into. And there's another interesting case you might run into, which is this. What is this? What is this n to the 0 power? Well, okay, we know from the rule, the general rule, right, that if I have something like this, I add the power, so I would get n to the 0 plus 5, and then 0 plus 5 is 5. So I notice that if I multiply n to the 0 times n to the 5, I just get n to the 5, which seems kind of weird, like, oh, nothing happened to the number. Well, here's why. Powers of 0. Okay, here's what you need to know. Anything to the 0 power always equals 1. Okay, not an exponent of 1, like literally the number 1. So if you see something like this, x to the 0, that equals 1. X to the 0 power, it equals 1. Okay, 5 to the 0 power, that equals 1. What if I have like a whole bunch of stuff? Ooh, 5x cubed and in parentheses next to the 0 power? This equals 1. What if I have a really big number? and I take that to the 0 power, it still equals 1. Okay, still equals 1. So in this case, right, here, like the rule applies, right? Like I could, even if I didn't know what a power of 0 meant, I could still just say, okay, I'm going to add these two exponents, and I still get the correct answer. But the other way to look at this is say, okay, well, n to the 0, this is just 1. This is 1 times n to the 5th, which is n to the 5th. Okay, and then just to show you a couple problems that you, kind of a couple problem types you might get. So let's say I get something like this. Here's a problem. So let's see. Here I have an x over here, okay. But on this side I have 5 to the 3rd times 5 to the 8th. So you can imagine, right? This is 5 times 5 times 5. This is 5 times 5, like 8 times. Okay, so this is going to be 5 to the 3 plus 8 is 11. So this is equal to 5 to the 11th power. So this should be 5 to the 11th power. So you would say, okay, x is 11. Okay, that's like just an example of a kind of problem type you might get. Now, on the flip side, look, what if I get this way? 3 to the 11th equals 3 to the 7th times x to the 4th. Okay, so I still have kind of this equation, and I still have an x in it. Let's just fix this. That's all we do. Okay, so let's look at this. So 3 to the 11th, this is 3 being multiplied by itself 11 times. This is 3 being multiplied by itself 7 times, and this is something being multiplied by itself 4 times. So what does this x equal? What does this x have to be in order to make this equation true? Well, notice all of these rules, the base is the same, right? Base is 6, base is 6, base is 2, 2, 2, base is x. So this needs to be a 3, right? And this will be 3 to the 7th times 3 to the 4th. Then 7 plus 4 is 11. So in this case, the x needs to be 3. Okay, and let me just show you one more, and I'm going to box this. And again, I'm just showing you kind of the different problem types you might run into. Kind of nice to have this. What about this one? This one's a little silly. A to the 8th equals a to the x. In fact, here, you know what? I'm sorry, let me do this. Let me make this a number just so we're not working with two variables here. Let's do this. 5 to the 8th equals 5 to the x times 5 to the 8th. What does x equal in this case? Okay, well, we know, like, if I have something like this, this plus this has to equal this, right? So x plus 8 equals 8. What does x equal? What plus 8 equals 8? 0. Okay, this was an exponent of 0.